So we are continuing our review for the final exam. In this example, a study explored whether a new drug, AZT, helps to reduce transmission of AIDS from mother to baby. Of the 180 babies whose mothers have been randomly assigned to receive AZT, 13 babies were HIV infected, compared to 40 of the 183 babies in the placebo group. So when you look at this, start thinking, like, what were the observational units or experimental units? Was this an experiment or an observational study? Okay, what are my variables? How many variables do I have? Okay, do I have one group or two groups? Okay. So first of all, what would the observational units or experimental units be? So it's called observational units if it's an observational study. It's called experimental units if it's an experiment. Okay. It looks like they're collecting data on the babies. Okay, so it talks about the moms, but I think they're just collecting the babies, collecting info on the babies of whether or not the babies had HIV. So I think it would be the babies, would be the observational units. Okay, and then the explanatory variable, what are they trying to use to explain? It looks like they're giving them AZT or not, because there's a placebo group, so they're getting AZT or not, and then they're trying to figure out whether or not they get AIDS. So the explanatory variable would be AZT or placebo, and that would be categorical. And specifically binary, there's only two groups. The response variable, what they want to figure out, what they want to kind of predict or explain, that's whether or not the baby gets AIDS. And that would also be categorical and binary. Now, once you know that you have two categories, come to your final exam formula sheet. Sorry, I meant to say two categorical variables. Okay. Notice right here under two samples, this is what we use two samples when we want to compare two groups. You have two proportions that are both categorical. It's the only thing on here where you have two categorical except for chi-squared. So the difference between chi-squared and just two proportions is that the chi-square test works if you have more than two categories. Okay. So if you only have two categories in each one, you're going to be looking at two proportions. So this is going to be a two proportions problem. And if you're looking at two proportions, then you need to use segmented bar graphs or mosaic plots. Okay. This one, you can see where they're kind of fat. This is a mosaic plot where the width is proportional to the sample sizes. And so looking at this, I can see the AZT group had a lot less HIV cases and the placebo group had a lot more HIV cases. So summarize what the plot tells us. I would say something like, in the sample, now it is important to say this is in the sample, not the entire population, but in the sample specifically, okay, babies with the AZT, or babies in the AZT group had, or were less likely to have AIDS, or HIV infected, sorry. Or I could have said that the sample proportion in the AZT group is lower than the sample proportion in the placebo group. So let's talk about, like, what would our sample be and what would the populations be? So basically we have let's come back up and look at our numbers. There are 180 babies that were in the AZT group. So the sample, we have two samples. So the 180 babies in the AZT group. And then we also had 183 babies in the placebo group. Oh, in the placebo group. So we had two samples. Two different samples from each group. And then we would actually have two populations. So we could have all babies whose moms were given AZT, and we could have all babies whose moms were not given AZT. Okay, so those would be our two populations. Now, how would we actually compare these though? Okay, so if we want to compare them, we would actually want to look at the population proportion for AZT and minus the population proportion of the placebo group. Now, maybe you would have wanted to do them in a different order. I just did AZT first. Okay. So this would be the parameter I'd actually be interested in, or we want to look at the difference in the population proportions. And if I want to look at the statistic, well, that would be our sample proportion in the AZT group minus the sample proportion in the placebo group. Okay. So in words, it would be the difference in the sample proportions. And let's see if we can actually calculate those. So in the AZT group, I have to scroll too much. In the AZT group, we had 13 out of 180 babies. So we had 13 out of 180. And then we'd minus the placebo group, which was, I think, 40 out of 183. Yep. Let's see what that gives me. So 13 divided by 180 is 0.0722. And then 40 divided by 183 is 0.2185. Let's subtract those. So we get negative 0.1460. So when we're comparing two proportions, what we're always looking at is the difference in those proportions. So we want to determine whether the data provide convincing evidence that AZT is more effective for a placebo for reducing mother-to-infant transmission of AIDS. State the appropriate null and alternative hypotheses in symbols and in words. Maybe it'd be easier to do symbols first. Or not, but let's practice doing symbols first. Okay. So the null hypothesis would be that my population proportions are equal. So the population proportion for AZT equals the population proportion for the placebo. Or you can write it like this. So I like to write that they're equal, but then you have to change it back to a minus. So the population proportion for AZT minus the population proportion for the placebo would be equal to 0. Then the alternative, what way do we want this sign to go? Okay, let's see, we want AZT to be more effective, and if it's more effective, there should be less HIV cases, right? So if it's more effective, there should be a less than sign. So then I could change it to, in symbols, in the subtraction, I could do pi for the AZT group minus the population proportion pi for the placebo group. And that would have to be less than 0. Now let's write it in words. We can say the population proportions are the same. That would be our null hypothesis. And the alternative is that the population proportion for AZT is less than for the placebo. Now, how would we actually find a simulation-based p-value here? Before I do this, and I probably should have just done it up above, let's hurry and make ourselves a little chart here, because I keep having to go back up to look at my data. So if this is my AZT, sorry, I want to do it like this. This is my AZT group, this is my placebo. Okay, and this is that they have HIV, and this is that they don't. And then we can have our totals. So there were 180 people in the AZT group, and there were 13 of them, okay, that got HIV. In the placebo group, there were 183 total, and there were 40 that got HIV. Now, one of the hardest parts of two proportions is you have to figure out what number comes here. So we're going to do 180 minus 13. Tells me that there were 167 babies in the AZT group that did not get HIV. And then we'll do 183 minus 40, which gives me 143 in the not group. So let's go ahead and add everything up here. So we have 53 in the that got HIV total, And 167 plus 143 is 310 in the not group. And if I add all of that up, I should get 363 as a grand total. Now that I have those numbers, it'll make it easier for me to say how we would do our simulation. So basically, we want to assume that the treatment doesn't do anything, right? That both groups are the same, and that the difference we saw was just chance of who was in our sample. Okay, so what we're going to do is we're going to assume that 53 babies wouldn't get HIV regardless of which group they were in. Okay, and that 310 babies would get it. Nope, I said that wrong. Assume that 53 babies would get HIV regardless of which group they were in, because there were 53 babies that got HIV, and 310 babies would not. Again, regardless of which group they were in. So, write HIV on 53 index cards, or like 53 blue cards, okay, and write not on 310 index cards, or like 310 green cards, however you want to do it, okay. Then shuffle them all up and randomly put, so how many people were in the AZT group? There are 108 people in the AZT group. So randomly put 180 in an AZT group and 183 in a placebo group. Okay. And then we would find the difference in sample proportions, and basically then repeat this thousands of times and see how often we get a sample difference in proportions as extreme as our statistic of negative 14 or negative 0.1463. So that's how you do the simulation. Now, obviously, we can't make you do that on the test, but I'd be very surprised if on the final she doesn't put something where you're choosing from multiple choice options of how would you do a simulation. Remember, we're just always assuming whatever we're doing that the null is true. So there's nothing interesting happening here, and we're just shuffling people into groups to see what would we get if they were just randomly shuffled. Okay, so now we can run the simulation. And this one, we remember we had two proportions, so we're going to use the two proportions applet. And let's see what I put in. So I entered the table, I clicked the box here so I could do a 2 by 2 table, and I put in the AZT group, placebo group, HIV not. Here's the numbers. Make sure that your totals match up. That's a really good way to make sure you put it in correctly. Click use table. And tell you how many times I've forgotten to actually click use table. I also like to click show table because then I get this nice observed table. Okay, and it will give you all kinds of useful information, like the conditional proportions, what proportion had HIV in each group. You can look at the bar graph up here or change it to a mosaic plot. Notice that it's doing the AZT minus placebo order. That was the order it came in, but sometimes you do have to change that there. It will tell you your observed difference is negative 0.164. So I didn't ask you, and I should have. Our statistic is, I think we're down the previous page, but p hat for the A group minus p hat for the placebo group gives me negative 0.1464. So that's your actual statistic. What though if you want to find your standardized statistic? So come back to your final exam formula sheet. You only have one formula for this, for anything you're going to do, where z equals your statistic minus the mean of the null distribution over the SD of the null distribution. And it's so nice that we have the simulation. We can do it easily. We just put in 10,000 shuffles. We shuffle. You can see on the most recent shuffle that my groups looked very equal. My shuffle difference in proportions was very small because my groups were so equal. You can see all of the different shuffled differences in proportions that we got, and you can see the mean and SD. So my statistic is negative 0.1464 minus the mean, which is always going to be 0 here. Because if the two groups are equal, under the null hypothesis, two groups are equal, so when you subtract the proportions, you'll just always get 0. Okay, and divide by the SD of the null distribution, so divide by 0.037. In fact, you'll see, when you come back here and do two proportions, your standardized statistic, we did write it out here, so it's the difference in your sample proportions minus 0 divided by the standard error of your proportions. Okay? And it says standard error of the proportions, okay? But we just read that straight off of our applet. So when we put in our calculator, we get negative 4.45. Okay. Now, could I find that up here? I could. It just depends on how big of a rounding difference there is. So they used the theory. Okay, so it's a little bit off. I probably rounded a bit more than I was supposed to. And the simulation just kind of ran on in each step. Oh, or I just typed it in my calculator wrong. If I don't type in my calculator wrong, I get negative 3.9567. Okay. So you'll notice my simulation one and my theory-based one, very similar, definitely close enough that you could get the right answer on multiple choice. See, my simulation p-value, well, what do I want to count? So remember your alternative hypothesis was a less than. Let's see right here, we're looking for a less than. So we need to be looking to shade to the left on ours, okay? If our statistic is negative 0.146, that would be over here, and then they're going to want to look for all the area to the left. But there's not really much there. But they're looking for less than or equal to negative 0.1464, and there was one time that that happened out of 10,000. So 0.0001. So this is your simulation on that row. Whereas this is your theory-based one, which happens to be the same. Let's interpret our simulation. Oh, let's interpret both of them. So for this one, we could say something like our difference in sample proportions of negative 0.1464 was 3.96 standard deviations below the mean. Or, so you could say like the mean, or you could say below 0, or you could say below the hypothesized value of 0. Yeah, all of those would mean the same thing. And your p-value is, there was a 0.0001 chance of getting our sample statistic, or our sample proportion of negative 0.1464, or less, because that was the direction we were interested in, if the null is true. Or in other words, if the population proportions are the same. Now, let's do our 2SD 95% confidence interval by hand. So our confidence interval, there's only one confidence interval formula on here, right here. It's just going to be our statistic plus or minus 2 times the SD of the statistic. And you'll notice right here where it says you can just read the SD statistic right off the simulated distribution, or you can estimate it with the standard error formula. You'll notice there is no standard error formula on this formula sheet because that would just be mean to make you calculate by hand because it takes a long time. So our statistic is negative 0.1464 plus or minus 2 times the standard deviation of the statistic that we just read right off the applet. So the mean, we're looking for the standard deviation, is this 0.037. So that's the standard deviation of all the various differences in sample proportions that we could have gotten. So the negative 0.1464 minus 2 times 0.037 gives me negative 0.222. If I add it instead, negative 0.07. And if I was going to interpret that, I could say something like, we are 95% confident that the difference in population proportions is between negative 0.22 and negative 0.07. Or you could be more specific to the context and say, like, babies in the AZT group are 0.22 to 0.07 less, because it was a negative, likely to get HIV than babies in the placebo group. And let's look at our theory-based p-value. So I just look right here where I do overlay the normal distribution so I can get the theory, which again is just 0.001. And we want a theory-based 95% confidence interval. So if you click this button right here for the 95% confidence intervals, this is always going to be your theory one. I don't know why that's the one they put in there. So it's negative 0.217 to negative 0.076. Is that right? Yep. So you'll notice it's pretty close to what we got when we did it by hand. The difference is truly just because simulation never matches up exactly with theory, because it just is based on what samples you happen to get. Okay. Let's see, was the theory-based approach valid? If you come back to your formula sheet, your validity conditions is that you need at least 10 successes and at least 10 failures in each sample. You might also want to think about it as the count in each cell of the two-way table is at least 10. So you can think about it either way. Okay. So we need at least 10 successes and 10 failures, or at least 10 in each cell in the table, not counting totals. So let's go back up and look at our table. Okay. So here's a spot where we have our table. We don't look at the totals, we only look at the actual data, which are these 4 cells here. So in the AZT group, we have 13 successes and 167 failures. In the placebo group, we had 40 successes and 143 failures. Or just all 4 of those numbers are at least 10. Super simple. So yes, all of our numbers are at least 10. And just to show you, how could you use our theory-based inference applet? So our theory-based inference applet, let's find our theory-based numbers. We put it in, we have to do 2 proportions. Group 1, you say there's 180 total and 13 yeses. This one's nice because you don't have to put in the failures, that 167 people that didn't get it. And it will calculate the sample proportion for you. Group 2 had 183 babies total, 40 had HIV. There's your sample proportion. Make sure you have the correct order so that we have the first group minus the second group. There's your difference in sample proportions. It does the segmented bar graphs for you. You need to click less than, make sure it's less than, and it's just 0 was in our null hypothesis and our alternative hypothesis. We compared them to 0. We put in our test statistic right here of our negative 0.1464. And then we're looking for all the area over to the left. And our standardized statistic, negative 3.95. Here's our p-value. It rounded it at 0. And if you wanted, you could do a confidence interval. So there's your confidence interval. So I do want to point out, look at the labels on the distributions of both applets. So this one said p hat 1 minus p hat 2. And if you look back up the simulation one, It said shuffled difference in proportions. Okay, so whether it says p hat 1 minus p hat 2 or shuffle difference in proportions, either way, it's all the various possible differences in sample proportions. That's what it is. It's the null distribution of all those various possible differences in the sample proportions. Now let's summarize our final conclusion that we could draw from this study. So we had a very small p-value, a very, very small p-value. So is it significant? Okay, our p-value is less than 0.05, so yes. Okay. What about estimation? We don't normally say put it here, but our best estimate of the difference in population proportions, that's just asking for your confidence interval, is that it is between negative point, let's just read off here, 21722 to negative 0.0755. So that's usually a very important thing your boss wants to know, of like, what is your best estimate for the difference in the population proportions? Okay, what about evidence? Well, our p-value is very, very small. I think we could say that we have very strong evidence that what? And now you repeat the alternative hypothesis that the proportion of all babies in the AZT group that get HIV is less than the proportion of all babies in the placebo group that get HIV. Now we want to know, well, what about causation? Can you say cause and effect? Well, to say cause and effect, you need a randomized experiment. So let's scroll way up to the beginning and see if it was. So way up at the very beginning, it says there are babies that were randomly assigned. So it does look like we did random assignment. Notice it doesn't say anything about if it was a random sample. Okay, so let's go back. So we need a randomized experiment. And in this case, it was. So yes, we can say cause and effect because it was a randomized experiment. Remember, an experiment just means we decide which group they're in. It's a randomized experiment if we randomly put them into the two groups. So generalizability, you would need a random sample. Okay, it didn't say that it was a random sample, and usually they will say if it was. So I'm going to assume we can only generalize to people that were similar to the sample. So you can't generalize to everyone if it's not a random sample. Let's try another one. So bleaching agents. In the garment industry, bleaching is an important component of the manufacturing process. Okay, so we have chlorine bleach, but we don't like to use it for environmental reasons. So we want to know, can we use hydrogen peroxide? So they have a low solution and a high solution. Okay. And it does say some shirts are randomly assigned. So that tells me it's an experiment. A high hydrogen peroxide solution, some are assigned a low one. The data values are the whiteness levels, and that's a numerical thing measured for each shirt. And the data file is on Canvas. It's called bleaching.txt. Okay. If you go to Canvas and you go to your final exam module, there's the data sets here. So you can open up the data set. Now again, Canvas does really weird things with the data set, so you probably want to actually download the data set before you try and copy it over. So just download it and open it up that way. So here's what my data set looks like. You would just copy everything and copy it straight over into the applet. So when it told me that my whiteness was numerical, that tells me that I have a quantitative variable. But we have two groups. or 2 samples. So coming to your final exam formula sheet, we have quantitative and we have 2 different means because we have 2 different samples or 2 different groups. So we're going to be doing 2 means for everything. And I want to use the order high minus low. We want to know if the high hydrogen peroxide creates wider shirts. Here's our summary statistics. So in the low group, there were 16 shirts. Here's your mean and SD for the low group. For the high group, 19 shirts. Here's your mean and your SD. And then the applet by default will put in this pooled. That just puts everything into the same, like everything into one pool and finds the sample size for everything, the mean for everything, the SD for everything. Okay. So what procedures would make the most sense for the situation? Well, that would be the 2 means. Okay. What kind of graphs? If you're doing 2 means, notice what kind of graphs. We can do box plots, histograms, or dot plots for each group. So we need side-by-side box plots, histograms, or dot plots. So by side-by-side box plots, histograms, or dot plots for each group. And we say side-by-side, sometimes that's vertical. Okay. So here are the 2 different dot plots and box plots. So here's our high on the bottom, here's our low on the top. Okay. Now, just based on these box plots, which group has the higher median? When you look at this, this is your median. This is your 3rd quartile. Not very good there. And the lower part of the box is your 1st quartile. This is your minimum, and this is your maximum. So if I want to compare which one has a higher median, well, here's my medians. It looks like the high group has a higher median. And which group has a higher inner quartile range? The inner quartile range is the length of your box. So it looks like the box is a lot wider for the high group, so it also has the higher inner quartile range. Let's see, what if we wanted to estimate the 5-number summary for the high peroxide? So we need our minimum, so that looks like it's about 83. My 1st quartile, I'd probably say 85. Median, 90. 3rd quartile, what's that, 95? And my maximum, I'd say 96. Okay, let's see. Coming back to this, what were our observational or experimental units? What did they actually collect data on? It was each shirt, where it was the experimental units. The explanatory variable was the high or low peroxide group. So that is categorical. Okay, also binary, there's only 2 options. The response variable is the whiteness. And it said that was numerical, so that means quantitative. My populations. Well, in this case, there's 2 populations. Okay, the first one is all shirts in the high group, and the other one is all shirts in the low group. And my sample, in this case, we have 2 samples. We have how many shirts did we have in the high group? We had 19 in the high group, 16 in the low group. So my samples are the 19 in the high group and 16 in the low group. And the parameter, we're comparing 2 groups. So my parameter would be the difference in population means. And my statistic would be the difference. Sorry, let me see. Difference in sample means. Now let's actually write those in symbols. So we could do the population mean for the high group minus the population mean for the low group. That would be my parameter I'm interested in. And my statistic, I would do my sample mean for my high group minus my sample mean for my low group. Now, suppose I tell you that the 95% confidence interval for this difference in the population means is negative 0.6 to 4.46. So let's interpret this. So we can say it a few different ways. We could say like, we are 95% confident that the difference in population means is between -0.6 and 4.46. Okay, or I could say like, we are 95% confident that on average, the high group is we'll say 0.6 less to 4.46 more white than the low group. Let's see, what does that 95% confidence level mean? We haven't actually talked about that for quite a while. So the confidence level means if I took thousands of samples and found the confidence interval for each sample, then about 95% of those samples would give me a confidence interval that actually contains the parameter, or the true difference in population means. Okay. The problem is there is no way to know if my interval, or my sample and my interval, is correct or not. So we know that 95% of the samples we could have taken would give us a correct one. So ours is probably correct, but we also know that 5% of the samples do give us an incorrect interval, and maybe ours was one of the incorrect ones. We don't actually know. Let's see, what else? Based on the interval, do you have evidence that the high concentration is wider on average than the low concentration? Okay. So anytime you're doing this to look at confidence intervals, you want to look and say, well, is the value I'm interested in the interval? Now, I did it this way on purpose because sometimes she'll do this. She won't give you the whole, like, write down your hypotheses. She'll just give you the confidence interval. Okay, and you have to kind of figure it out. Okay, so let's figure out, what would our null and alternative hypotheses have been? The null hypothesis would have been that the difference between the groups was just equal to 0. It's always equal to 0. And the alternative would have been that the high group, if you do the high group minus the low group, well, let's see, we want the high group to be wider, so this should be greater than 0. Okay, so what we want to do is we want to see, is 0 in the interval? And yes, 0 is in the interval. In fact, when you look at our interpretation, we said, well, the high group is either 0.6 less or up to 4.46 more. So it's kind of hard. You're like, well, is it less? Is it more? You can't really decide. And that's how you know that they're probably just the same. Okay, but because 0 is in the interval, 0 is a plausible value. Okay, so it is plausible that the population means are the same. Okay, or we do not have evidence that the high group mean is greater than the low group mean. Okay, so we don't have evidence, and in case you were going to wonder, we do not, or it is not statistically significant. So statistically significant always means you have a p-value less than 0.05. We said it's plausible. That means we would have had a big p-value. So it's not statistically significant. Now that we've done all that, let's go ahead and practice writing our null and alternative hypotheses. Okay, and we already wrote them in symbols up there, so let's just write them in words now. Our null hypothesis would be that the population means are the same, and the alternative hypothesis would be that the population mean for the high group is greater than the population mean for the low group. And I wrote it in symbols with the subtraction. You could also write it like this. We could do the population mean for the high group is equal to the population mean for the low group. Or the alternative, we could say the population mean for the high group is greater than the population mean for the low group. Okay, so now let's use our two means, applet. Actually, no, I believe it's called multiple means. Okay, it is called multiple means, not two means. Again, the formula sheet is so nice. It will tell you this is the applet that you need to use for a simulation. So to put everything in, I just paste the data. The problem is when I pasted my data, it didn't show up right, and I realized, oh, my response, my numbers were first. So I had to click on this button to switch which variable was which, and then it all worked. Okay. It automatically sorted off the groups and everything for me. I didn't have to do a lot. I did click add the box plots. Make sure your statistic, you're looking for the difference in means. Here's your summary statistics. Again, pool just means it puts everything together and finds the overall mean in SD. Okay, this is your statistic. Your difference in your sample means. So I don't think we wrote that anywhere on this problem yet. Our statistic is X bar for the high group minus X bar for the low group, and it is 1.931. Then we can do a shuffle our options. I did 10,000. Our hypothesized difference in the means is just 0. I shuffle responses. Okay, this is your most recent shuffle. You can see that their difference in means was really small. And to count my samples, I picked greater than, because our alternative hypothesis said a greater than. You put in your statistic of 1.931, and you get a simulation-based p-value of 0.0684. And I don't know why this applet, they didn't put on a theory-based one. So all the other applets they didn't on this applet, though. So that's just our simulation p-value. So from the multiple means applet, let's find our standardized statistic. And so again, that's just z equals our statistic, which is 1.931, minus the mean of my null distribution, so 0.011. Now theoretically, you could put 0.011 there, or you could put 0 because we know it was supposed to be 0. You can do either one. Your answer is going to get close enough for a multiple choice test. Okay, and divide by 1.322. So because I don't want you to have to remember it, just read it straight off the applet. Just put in the 0.011. It's not going to hurt anything. But 1.931 minus 0.011 divide by 0.13 or 1.322. So I get 1.45. Now let's see, what about my simulation-based p-value? My simulation-based p-value is 0.0684. And my theory-based p-value, I can't get not from this applet. So not this applet. What about a 2SD 95% confidence interval? So we need to do our statistic plus or minus, oh, you know what? I wrote Z here for multiple means. Remember, we're actually supposed to do a T. If you forget that, it's not going to be a huge deal. Okay, statistic plus or minus 2 times the SD of the statistic. Okay, so my statistic was that 1.931 plus or minus 2 times the SD of the statistic. Again, you're just reading it straight off of the applet. You don't have to do anything else, so just 1.322. So let's see what this gives me. 1.931 minus 2 times 1.322 gives me negative 0.713 to 4.575. And to look at my theory-based, you could go to your theory-based applet. But on this applet, it does have this 95% confidence interval. This is a theory one, theory-based. So it's negative 0.5959 to 4.4577. Now, this is your theory-based inference. So we have two means. Make sure you click two means, otherwise it just starts with one proportion. And I put in my two groups. I just happened to put in the low group first and my high group second. Not on purpose, it was just the way I put it in. So then I needed a change, because remember, we're supposed to be doing high minus low. So I clicked this button to change it so it was group 2 minus group 1, so that they were in the right order. I clicked that I want to do greater than 0. And I get my statistic of 1.56, and I get a p-value, and I can do a 95% confidence interval. So this is our theory-based applet. Let's see. What would have happened if I'd accidentally switched? If I switched this order and it would have been group 1 minus group 2, remember, what would have happened? Your statistic would have switched signs from negative to positive, but your p-value would have been exactly the same. And your confidence interval, you would have just switched signs. Okay, I kept talking, but it was paused, so I already have it written out here. Let's look at our conclusion based on the fact that the p-value is 0.0646. So it's 0 plausible value for the difference in population means. Yes, because that's a big p-value. So big p-value means your null is positive. Your null is plausible. Okay, what about evidence? We can say there's little to no evidence that on average the high group is wider than the low group. So no evidence for the alternative hypothesis. What about statistically significant? Well, a big p-value means no, it's not statistically significant. What about cause and effect? Yes, because remember we said at the beginning it was a randomized experiment. What about what can you generalize to? So generalize, you need a random sample. Okay. It didn't say where they got the shirts. If the shirts are a random sample of all shirts. Okay, so maybe if they only do a certain kind of shirt, maybe that's different than other kinds of shirts. Like maybe a high peroxide would work better on some types of shirts than other types of shirts, okay? So we can only generalize to similar shirts as what's in our sample. Let's see, let's do a little bit of theory here. What would happen to our p-value if all of the whiteness scores for the high group were magically 4 higher? So let's pull up the applet. I want to let us actually visualize. So I pulled up the applet. I heard him put in all of the numbers. You do need to click and do group 2 minus group 1. Okay. So this is what it looks like now. Okay. So I want you to visualize, though, what would happen if all the whiteness scores for the high group were magically 4 higher. So group 2 would suddenly become 4 higher. Okay. So if this number becomes 4 higher, if everything becomes 4 higher, then the mean will be 4 higher. And if this number is 4 higher, then wouldn't my difference also be much bigger? So instead of having a difference of 1.93, my difference would now be like 5.93. That would put you way over here. Wouldn't that give you a really small p-value? Or if you want to visualize it with these two, they're kind of like a visual thing of a confidence interval. The mean would go up another 4. So these groups would be very different from each other. Okay, so I think my p-value would get really small. Okay, it's pretty easy to test. What would that actually be? Just add 4 here. So what would be 93? And click calculate. Yep, so there's my statistics, 5.93, and notice my p-value is now basically 0. Let's switch back. Now, what's the next thing it asks me to test? It asks me what would happen if the low group were magically 2 higher. Well, let's think about this. If my low group became 2 higher, then this would be 89. So we'd have 89.44 or 89.37. Those would be very similar, right? So if I had 89 here, and then click calculate, my difference is now almost 0. And look, what's my p-value? 9.95. It's huge because the means would be almost the same for both groups. So we'd have a really big p-value. What if I changed my standard deviations? So what if my standard deviations for each one became like 7? And 9. Just to put a random number in. Notice my p-value is now 0.48. So instead of 0.06, it's 0.48. So my p-value got a lot bigger. The reason why is bigger standard deviations, okay, give you a lot more uncertainty, and so you just can't be as sure of anything. So your p-values are a lot bigger to reflect all that uncertainty. Okay. And the last thing we ask is, what if both of your sample sizes were larger? So even if I kept these standard deviations the same, what if I just put in 100 for both of my sample sizes, or let's say 190, and I click calculate? Okay, my p-value got really small again. Okay, so let's come back and write our notes. Okay, so if all my whiteness scores were magically 4 higher, then the sample means are farther apart. So that would be a smaller p-value. Okay, but if all the whiteness scores for low group were magically higher, then the sample means, oh, sorry, I said the samples are farther apart, but I didn't mean to say means. So if we made them closer together, so if the sample means are closer, then we'd have a bigger p-value. If both of your sample variations were larger, well, bigger SDs mean more uncertainty. So bigger p-values. You can't be as sure of something if you have just more standard deviation. And finally, if both of our sample sizes are larger, we know no matter what we're doing, bigger sample sizes mean smaller p-values.